To try to develop some more techniques of integration, we're going to take the differentiation techniques that we know and try to undo them. So the first one, it will be the chain rule. We're going to try to undo the chain rule, and the method that we're going to come up with is called substitution, or u-substitution. Consider how we take the derivative of e to the x squared. Well, it's an exponential function, e to something, and so we write down e to that same thing, but then the chain rule tells us we have to multiply by the derivative of the exponent, and so we get 2x e to the x squared. And therefore we know that the antiderivative of 2x e to the x squared is equal to e to the x squared. This is blindingly obvious from the previous line. However, if we didn't see the first line, then the second line is not obvious, and so we don't really know how we should be approaching this integral here. The goal of substitution is to replace a complicated integral with a simpler one. That is, we want to replace a complicated integral with one which appears on the list of basic integrals that we've memorized. To see how this is done, consider this integral that we were trying to compute just now. Well, we only have one basic integral involving exponential function, namely this one here. The antiderivative of e to a variable is just e to that variable plus c. So it's natural to try to replace this exponent x squared with just a single variable, u, let's call it. Okay, so let u equal this exponent, x squared. Then I can rewrite the integral by replacing x squared with this letter u. But it's important that we realize that we can't really proceed until we've replaced all the occurrences of x and its differential dx with expressions involving the new variable u and its differential du. So how do we replace the differential dx? Well, we use our substitution and we compute the differential of both sides. So in this case, du will be the derivative of x squared times dx, and that's just 2x dx. Okay, well then, what was remaining in this integral to get rid of? We had 2x dx. Okay, but here we see that's equal to just du, so we can replace that with du. Aha, now here we have an antiderivative, e to the u du. That was one of our basic integrals, and so we can simply say that is e to the u plus c. The only thing left to do is to back substitute, namely, we take our answer and we replace all occurrences with u with occurrences of x again. And in this case, we take our e to the u and replace u with x squared to get this answer. And so this is how we should have approached this integral to begin with, if we hadn't already taken the derivative of e to the x squared. So let's summarize this method. What we do is we make some suitable substitution, which is something that admittedly does require practice, and then we compute the differential, du, by computing the differential of both sides of your chosen substitution. Next, we rewrite the integral with no occurrences of the original variable of integration. And to do this, it's sometimes helpful to solve for x or dx in the equations you're using to define your substitution and the differentials. Okay, by now hopefully you've got an easier integral to evaluate. Otherwise, you're just going to have to try another substitution. And once you've evaluated the integral, don't forget to change back to the original variable, because if a question is posed with a certain variable and you give an answer involving a second variable, that's sort of a nonsensical thing to do. You really do need to give answer in terms of the original variable. Now, unfortunately, this technique doesn't really work on all types of integrals. For instance, it will not work to compute this integral. In fact, no integration technique that we encounter in this course will allow us to compute this antiderivative. On the other hand, sometimes more than one substitution will work. The next example is such a case. So let's try to compute this integral with the method of substitution. What I'm going to do is let u equal 2x plus 1. My reasoning for doing this is that I know how to take the antiderivative of square root of x, and so I want to replace the thing underneath this square root with just a single variable, u. Okay, so that's my substitution. Let's try it and see if it works. We need to compute du. We need to compute the differential. Well, the derivative of 2x plus 1 is 2, and so the differential of u is 2 dx. Alright, now we're ready to try to replace all occurrences of x with occurrences of u. And to do this, I find it convenient to solve for dx in this equation. And now let's see what happens. Well, the expression out of the square root was u, so I replace that with u. And dx is just du over 2, so I replace dx with du over 2. And now this is a simpler integral. We can factor out the 1/2 and rewrite square root of u as u to the 1/2, and now use the power rule. Don't forget to simplify, and then back substitute. At this stage we need to look at our answer here and replace u with 2x plus 1. And so this is what we get. Let's do the same example, but using a different substitution. Let's see what would have happened if I'd let u equal the square root of 2x plus 1, which is equal to 2x plus 1 to the 1/2. Well, then du is what? It's the derivative of this expression times dx. So there's the derivative and simplified. So this is du simplified. And we can solve this for dx by multiplying both sides by this square root expression. And I can even simplify this a bit further. If I recognize that this square root expression is my choice of u, that means dx is equal to u times du. And therefore I can rewrite the integral. This square root expression is equal to u, and dx was equal to u times du. Okay, that means I'm taking the integral of u squared du. This is an easy integral. Use the power rule to do it. And then don't forget to back substitute. Remember, u in this case was 2x to the 1/2, sorry, 2x plus 1 to the 1/2. That raised to the third power is 2x plus 1 to the 3/2. And so we get the same answer as last time using a different substitution. Okay, let's do another example. In this case, we already know one technique for computing this. We could go ahead and multiply out this binomial completely, except that would take forever, right? I mean, this would involve more than 100 terms, so that's probably an inefficient way to compute this integral, although that is how most computers would do it, I believe. Anyway, how are we going to do it? Well, we know that if I have just a variable raised to some constant exponent, then we can compute the integral. So let's try to replace the thing being raised to the exponent, namely 5 minus x. Let's make that a new variable, u. Okay, then what? Then du would be equal to negative 1 dx. Alright, well then that means dx is negative du, and we can rewrite our integral. The expression in the parentheses is u, and dx is equal to negative du. So our new integral is u to the 100 du, which is easier than the original. Okay, so let's use the power rule to compute that antiderivative, and then back substitute. Okay, the following integral is going to involve a trick which is nowhere near obvious. I do not expect you to be able to do this on your own, but I'm going to show you how to compute the integral of secant x using the substitution rule and a clever trick. And once we do this, I will simply have you memorize the result, because let's face it, the antiderivative of secant x should be something that we are able to just recognize, right? Such a simple function. We should just know it's an antiderivative. So let's try to develop it. What is it? Well, the trick is to multiply top and bottom by secant x plus tangent x. Far from obvious, but let's do it. Well, then we multiply the secant x to both terms on top to get secant squared x plus secant x times tangent x. Now, I'm going to let u equal the denominator here. Then du is the derivative of this substitution, which is what? Derivative of secant x is secant x tangent x, and derivative of tangent x is secant squared x. So the differential is that times dx. Okay, but recognize that that is just the numerator here, isn't it? Secant x tangent x dx is just this numerator here, and in fact u was just the denominator. So it looks like I can replace the original integral with now the integral of du over u, which is much simpler. In fact, this is one of the basic integrals we know. It's natural log of absolute value of u. And now we're ready to just back substitute. And so now this boxed formula is a formula which you should add to your list of integrals to memorize. And similarly, the antiderivative of cosecant x can be computed. This time there's a minus sign, so be aware of that. Now there's an added subtlety when we're trying to compute definite integrals using the method of substitution. You see, when we write a definite integral of f of x dx from a to b, then a and b are understood to be values of x. Or if it was some function of t, then a and b would be understood to be values of t. So when we make a substitution, replacing the variable of integration with u, the limits of integration need to change according to that substitution. Okay, let's try this definite integral. So in this case, I'm going to need to make a substitution to evaluate the integral, but I'm going to need to modify these limits of integration accordingly. So let's start by letting u equal natural log of x. Now I'm doing that because of experience. I know that this substitution will lead to something good because du is 1 over x dx, and in the integral here I have 1 over x dx, and so I feel like that'll be a good choice. Okay, let's solve for dx in this equation by multiplying both sides by x, and now let's rewrite our integral. Natural log is just u, and dx is equal to x du. And I can see that these x's will cancel. Now I want to point out here that since I have u and x appearing, it would be ambiguous to just say integral from 2 to 10. Here I do have to explicitly state that it's x, which is ranging from 2 to 10, because two different variables are appearing here. Okay, and the next step, I can go ahead and replace these ranges for x with ones for u. So if x equals 2, then u equals natural log of 2 using our substitution. And if x equals 10, then u equals natural log of 10. Okay, at this stage, however, this second line, it's not necessary to write u equals because there aren't any x's appearing in the integrand. Here it just says u du, and so it's understood that these limits are values of u, not x. Okay, so let's go ahead and compute an antiderivative. We get u squared over 2, and then we're going to evaluate that from natural log of 2 to natural log of 10. So we just go ahead and do that. Plug in natural log of 10 for u, and then natural log of 2 for u, and subtract. And this is the value of that definite integral. Okay, let's do that same integral again, except I'm going to do some things slightly different. So let's start by making the same substitution. Then du equals 1 over x dx, and this time instead of solving for dx, what I want to do is simply notice that my integrand already looks like natural log of x times 1 over x dx, and so this is my u and this was my du, so I don't really need to solve for anything. I simply replace that with u and that with du. At this stage I do need to explicitly state that it's x ranging from 2 to 10, or I could simply say from natural log of 2 to natural log of 10 like I did in the previous example. However, in this solution I want to point out that you don't actually need to change your limits of integration if you back substitute before doing the evaluation. So let's do that. Alright, so we take our antiderivative, and in the previous case I then plugged in natural log of 2 and natural log of 10 to this expression, but in this case what I'm going to do is simply back substitute. And so you see this whole time I'm sticking with the same limits of integration being x values. This is fine to do if we do this back substitution, because now I can plug in 10 for x and 2 for x, and I get the same answer as last time. So these are these two techniques that you can do to do definite integrals using the substitution rule. You either back substitute, or you have to change the limits of integration to values of u rather than x. To recap, our second integration technique is called substitution, or u-substitution. Choosing the right substitution does require familiarity with which substitutions generally work and which generally don't, and the only way to learn this is by practice, so please do as many exercises from the book as you can. When you're computing definite integrals via the substitution method, it is important to be aware of and make sure you're writing unambiguously which variable ranges between which limits of integration. Now in the next video we're going to describe another integration technique, but before you do that, here are your questions for the day. And I will see you in the next video.